Good afternoon, sir.
Good
Good afternoon,
afternoon, sir.
sir.
Good afternoon, sir.
Good afternoon. Okay, fine. So in this session, we can start the next model 2. So the first definition, what we are going to discuss in the first slide, that is the title. Okay, title of this model, that is vector space. First, we need to come to know what is the definition of vector space. It's quite easy. Many of the guys would have already studied this in your schoolings. Hope you can remember it. Otherwise, not an issue. So here, vector space, it's related with a set. Okay, that set has to be a non-empty set. Please keep in your mind. That non-empty set has to satisfy some algebraic operations. Okay, what are all the operations? First operation it has to satisfy, that is vector addition. Okay, vector addition and then scalar multiplication. Totally it has to be satisfied two properties. One is vector addition, another one is scalar multiplication. If it satisfies those two properties means, then the given non-empty set is called a vector space. Okay, so vector addition, scalar multiplication. Okay, so in each condition, in each operations, it is having some properties. Okay, if it is a satisfying vector addition means it has to satisfy four conditions. What are all the four conditions? What are all the four axioms? In vector addition, it has to satisfy the commutative property, associative property, and then identity property, or in another way you can call that as a zero property, zero vector property. Okay, already you have learned that identity axiom. The same process only here also you are following here, but because of the different authors, they are used that as a zero vector property. Okay, third one. Last one is it can be called in two ways. One is inverse property, inverse axiom, or negative of the vector property, negative vector property. Okay, totally four rules: commutative, associative, identity, and then inverse. Okay, so instead of identity, you can better call like zero vector. Okay, instead of inverse, you can call that as a negative vector property. So if it is a vector addition means it has to satisfy these four conditions. If it is a scalar means, again it will come with another set of four properties. What are all the four properties? Okay, first property is distributive property. Okay, next one is distributive property with respect to a scalar addition. First one is with respect to the vector addition. Why they are called that as a vector additions means here you are used there two vectors. Okay, one scalar where k is a scalar, but in your second property, that means the sixth property, you are used there two scalars, only one vector. So this is related with the scalars, this is related with vectors. So that's why they are just splitted in two ways: distributive property with respect to a vector addition, distributive property with respect to a scalar addition. Third one is associative with respect to a scalar multiplication. Why they have kept the name as scalar multiplication means they have used here more dominantly like two scalars. Okay, last one is just one product property. Okay, that means 1 into x equal to x. That always will be true. Okay, nothing to worry. So, but if it is a scalar multiplication satisfies means it has to satisfy these four properties. If it is a vector addition means it has to satisfy these four conditions. So, by cumulatively, if we could see if it satisfies two properties in general like a vector addition and then scalar multiplication, then the given non-empty set is satisfied the vector space properties. Okay, So now with that we can enter into the problems directly, how the way it can be easily verified. Okay. So here in this problem, they are given the question like set of all M2 cross 2 forms a vector space. Forms a vector space means here you need to check two conditions. One is vector addition, another one is scalar multiplication. You have to verify both the cases. So in which any guess, what does it mean of M2 by 2?
2 by 2 matrix.
Very good. So it can be any matrix with a dimension 2 by 2. So accordingly we can start assume like in your vector additions you have to satisfy first four conditions. First one is commutative. In your commutative property verification there must be needed two elements from the set, from the non-empty set. So here two elements means two matrices I need to pick from that M2 by 2. First matrix I can pick as A. Okay, that means like A, B, C, D. Okay, this can belong to M2 by 2. By the same way, I can pick like sometimes this question can be asked as a 10-mark question, so please keep listen. This is quite easy. Just you are going to verify the properties of vector addition and then scalar multiplication. Okay, so next one is defining the next matrix from the same set. Next maybe E, F, G, H, that also belongs to 2 by 2. After this, so first property I need to check commutative. So commutative means I have to prove according to the definitions what we have defined there in the preceding steps. So here A plus B equal to B plus A. That is the condition they are given there in the commutative property. X plus Y equal to Y plus X such that X and Y are the members of the non-empty set. So here A and B the members of that matrix M2 by 2. So let me check the LHS. Very easy process, so please listen. A plus B equal to AB CD plus B E F G H. Okay, so it can be added directly with respect to the positions like A plus C, sorry, A plus E, next B plus F, C plus G, next D plus H. Okay, so it has to be proven like equal to B plus A. Any guess how the way I can proceed further? Any idea?
First the B matrix, then matrix.
Sir, you can interchange the position of E and A.
So I am allowed to interchange the positions of A and E. Then definitely the value will not be varied. So I am freely vary the positions of E and A. Likewise, I can follow the same in the second part also. In the second row, first element like G plus C, then H plus D. After this, I can split it separately like E, F, G, H plus A, B, C, D. Okay, so it is well splitted like this is the first part, that is B, this is A. So you have proven commutative axiom is true. You have to write that word here. Commutative property is true. Have you understood this property proving part? Is it clear?
Yes, sir.
Okay, because I'm not going to follow the same procedure of solving in the next properties. I can say in general, you have to try by own. That's your task. Okay, next one is we can come back and then check what is the second property, that is associative property. So how many matrices are needed? Three matrices are needed in our problem. So definitely I need to define another one matrix, that is C. Okay, so C equal to, I can define like H, I, maybe J, K, L. Okay, so this also will lie in the matrix set M2 by 2. So here, any guess what I need to prove here in the associative property?
Sir, A plus bracket B plus C
Very good.
equal to
Equal to
A plus B plus C in bracket.
very good. That's it. So I hope you can able to complete this by using the above three matrices. Can you able to complete this? Yes or no? It's quite easy to complete it, right? Please respond so that I can confirm it. Otherwise, I'm ready to solve it.
Yes, sir.
Okay, so simply you can copy the values of matrices A, B, C, and then you can change the positions as you followed in the first commutative property. Okay, so that's your task. Third one, that is uh, zero vector property. Zero vector property means first I need to define the zero vector here. That is, let me define like O. Okay, that is 0, 0, 0, M2 by 2. So I need to check the property like A plus 0 equal to 0 plus A equal to, what will be the answer?
A.
A. Then zero vector property is well satisfied. See here, x plus 0 equal to x, 0 plus x equal to x. So this is true. So this property also proven. So the last property we need to check, we need to close that vector addition thing, that is negative vector property. Negative vector property is nothing but x plus minus x. So that means, so here, so you can write here a zero vector property is proved. Last one is, so I can take minus A as same, minus A, minus B, minus C, minus D. Okay. After that, so you can simply check to prove that, or you can write like A plus minus A equal to minus A plus A. What will be the answer? What will be the answer?
Zero matrix.
Zero matrix. Very good. So you can, you have to write at least one side proof like A plus minus A. Okay, that is a good presentation in the 10 mark wise. So by satisfying all the four conditions, I can confirm here, here vector addition algebraic operation is proved. Okay, for the set, for the non-empty set M2 by 2. So vector addition property is proved. Okay, only one more property we need to check. I'm not going to solve it, so I can just simply say the hint to complete it. So please listen. So second one is scalar multiplication. The same process here also you are going to follow. Scalar multiplication, there we can cross check what are all the things we need to introduce further. Okay, so however you are going to use only two matrices to prove all the four conditions of scalar multiplications. So just you can make use of the above defined two matrices. So the first property is like, first property, what does it mean? Distributive with respect to vector addition. Okay, second one is with respect to scalar addition. So now that means instead of x plus y, you are going to use here what? K into by rearranging the terms of the definition with respect to our problem, how the way it can be rearranged. Instead of
A plus B.
that's it. Very good. So instead of x plus y, you are going to use here k into a plus b equal to ka plus kb. Definitely it will be true. Okay. So here k is any scalar. Okay. Here nothing to keep as a scale separate numbers. Just you can keep it as a k itself. Then you have to mention that k is a scalar. Okay, that's more than enough. Next, second condition, you need to check with respect to a scalar addition, that is k plus l into x equal to kx plus lx. Okay, so how the way it can be verified? So that is k plus l into a equal to ka plus la. Okay, so this is also quite easy process. The last one is k l into a, I think. Okay, k lx. Okay, so that means k into la equal to kl into a. Okay, last one is very easy. 1 into a equal to a. Okay, by verifying all the four conditions, you can conclude that the m 2 by 2 satisfy the operation scalar algebraic operation scalar multiplication. So in general, by solving these two algebraic operations, you can conclude that it forms a vector space. Is it clear on this problem? Is it clear? Have you understood this problem?
Yes, sir.
Okay.
Yes, sir.
Yeah, before getting to the next problem, you can please fill the attendance form very quickly, then we can move on to that. Please fill the attendance form quickly. Okay, fine. Let us enter into the last problem on this vector space model. Okay. So here, the polynomials of degree less than or equal to n forms a vector space. So here also you need to check two properties, two algebraic operations. One is vector addition, another one is scalar multiplication. Okay, so first one we are going to check. First I need to define three things. Okay, how the way it can be defined, that means polynomials of the degree less than or equal to n. So first I can start with like a. I can choose like a. So let a equal to a0 a1x plus a2x square. It can go up to, any guess?
ANXN.
Very good. ANXN. I should not exceed to that because it is restricted up to n. Okay. Next, b equal to b0 b1x plus b2x square plus bnxn. So to prove a vector addition in the case of distributive, definitely it is required three terms in the set. So I can choose another polynomial equation also so that it can be easy. Okay, after this, so I can start check the commutative property. So that commutative property to prove that a plus b equal to b plus a. So first I can write the terms like LHS equal to a plus b equal to, many of the guys have already maybe you have predicted how it can be proven easily. Nothing to get any complex on this because it's quite easy. So a plus b equal to a0 a1x a2x square anxn. So b0 b1x b2x square up to bnxn. So from which I can choose like a naught plus b naught. Next a1 plus b1 into x, a2 plus b2 into x square. Last one is an plus bn into x to the power n. Now I should say a plus b belongs to the rule of the polynomial equation formation. Okay. Further, it can be splitted in the way like b naught plus a naught, then b1 plus a1 into x, b2 plus a2 into x square up to bn plus an into x to the power n. So further it can be splitted like b naught plus b1x plus b2x square up to bn x to the power n. So next one is a naught plus a1 up to an x to the power n. So the last term is I can easily say like it is b, it is a. So commutative property is proven. Okay. So by using the same procedure, you can derive for associative and then zero vector property. Last one is negative vector property. Okay. So after solving it, you can proceed to the process of proving the second algebraic operation, that is scalar multiplication. There also you need to prove 4 conditions with respect to the multiplications. Okay, that's your task. So because if you are understood the only one property proving part, means it is quite easy to prove the remaining parts also. Okay, so one more definition with that.
Excuse me, sir.
Yes, please.
So
Yes.
for the 0 1, sir, we need to show like 0 plus 0 into x plus 0 into x square, or just
Exactly.
0?
Just a 0. It is not required to write in a complete up to xn. So because that is nothing but 0. But any 0 element, any 0 number can be written in the polynomial way. That's what they try to say. Simply you can mention that like 0 belongs to polynomial equation. Something you can define that as a set name like m or something like. These are belongs to m, m of n or something like, that's your wish. Otherwise better you can use a symbol p of n, otherwise p suffix n. So if you are using this set notation, means simply you can use there in the position of 0 vector, instead of writing the whole term you can write directly like p of n. Can you understand what I am trying to say on it?
Yes, sir.
So better it is advisable to use one set notation. Either it can be p suffix n or p of n. That is, both are acceptable, universally acceptable. Many of the authors are used p of n. Some authors may be used like p suffix n. that gives polynomial of degree n. Okay, so only one small definition with that I'll close. So please listen. Next definition is subspace. Okay, a subspace is it's a subset. Okay, so in your previous thing, you are discussed like V is a non-empty set. It's a set. Listen carefully. It's a set. It follows two conditions like vector addition, scalar multiplication. Then it is called like a vector space. Now they are saying the definition for subspace. Listen carefully, subspace. A subspace, it is derived as a subset of the vector space. Listen carefully. One subset I am going to choose, that is a W. It's a subset of V if W satisfying again the same conditions like vector addition and then scalar multiplication means, then obviously W also forms a vector space properties. Because of the subset reason, it is called like a subspace. Have you understood this definition? Is it clear? Is it clear? Have you understood this definition, subspace definition?
Yes, sir.
Okay, so but here they were mentioned one sentence. It is not required to verify all the properties of the vector space. Why? Because it is a subset of the vector space. So it is not required to verify all the properties. Instead of verifying all the 8 conditions in both the cases, simply you can, it is enough to verify only 2 properties. What are all the properties you need to verify? That is, the theorem is defined. That is, one property you need to check x plus y. In that case, can you just guess what property will be proven, either vector addition or a scalar multiplication? If it is a true for x plus y means, what condition it can try to reveal, either vector addition or scalar multiplication? I'm repeating the same question to you. See here, we are just taking a W is a subset from the vector space V. Then it is not required to verify for the elements of W all the conditions of the vector space. Instead of verifying all the properties, it is enough to verify only 2 conditions. First condition is x plus y condition. Second condition is kx condition. So now can you please try to connect x plus y condition related to whether it is connected with vector addition or scalar? Vector addition, very good. So obviously kx will connect with scalar multiplication. So if one set is given, it is asked to check whether it is a subspace or not means, it is more than enough to verify only these 2 conditions. One is x plus y condition, another one is kx condition. Please keep this in your mind, because by following these 2 properties only, we are going to solve in the next class of problems on subspaces that can be discussed in the next class. If there is any doubt up to this part, you can please interact with me, otherwise we can conclude the meeting. Okay, fine. Okay, thank you. We can conclude the meeting. Thank you all. Thank you.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.